Right, let's start the simulator. So we'll start a new project and we'll call it test, and we'll select a location. And we'll choose the we'll choose the ATTiny13. And you can see that the assembly file has been pre-populated. Very useful actually, including things like this is a nice touch. Press F2 and you get the pin out. But also, all the interrupts and everything like that, all the vectors, all very straightforward. So that's lovely. I'm just going to assemble this, not that there's really anything in it, just to show you that. I'll just quit from here, just to show you what's produced. So we've got our assembly file, which is just a text, our hex file, the assembled version, list file, which we'll be stepping through, and then the project file. Yep, so pretty straightforward way of starting a project. Right, so let's start our simulator again. This time we already have the project there, so we'll go to Open Previous, and it's called Test. And I've just added some fairly basic assembler commands in there so that we can see what the effect is on the assembling and simulating of this program. So the commands are as follows. I load decimal 64 into R16, and that should be a hexadecimal value of 40. Then we move that value to R1, we clear the R16 register, we move the R1 value to R2, we rotate right. So rotating right should mean that the decimal value 64, which corresponds to the binary that you can see here, when we rotate right, that one value just switches to the right there, and so it's effectively halving the value from 64 to 32. What we'll see is hexadecimal 40 going to 20. Alright, so that's what we're expecting there. And what happens after that? So then the value from R1 will be moved to R16, the value from R2 will be moved to R17. So then we should have those two values there. We will halve that value again in R17, and that'll leave the R2 registers still with the original value. We'll do a subtraction, and then we'll clear everything and start again. So just a little bit of binary arithmetic basically. So we'll assemble that and simulate and keep an eye on those registers in this area here. So our main ones that we're going to be using are R16 and R17 here, and we're going to be using R1 and R2 here. Alright, so we'll do the update after every instruction, and then we'll just step through it. So the program starts after the chip has been reset, and it just jumps to main as our first instruction. So there we go. We initialize the stack, we set interrupts, then we're into our main program. So let's step through it. So what we're expecting to see is 64, which is hexadecimal 40, appearing in R16, which it has. Then we want to move that value to R1, so it should move over to here, and it does. You can see though that it's still there in R16, so the next instruction is to clear R16, step. Then we're going to move the value that's in R1 to R2, so that 40 should appear over here, and it does. Here's our rotate to the right of R2, so the 40 here should change to a 20. Yep, that's good. Then we're going to move these values back into R16 and R17, so there goes 40 to R16, there goes 20 to R17. We have another halving now of R17, and that shouldn't affect where it came from, which it doesn't. So R2 is still 20, but this value, which was in R17, now switches to 10. We then do a subtraction from R16 of R17, so this should go to a value of 30, which it does. And then finally, we just clear all of those registers, clear, 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 and start again. and we can run and it'll just do that happily forever. So that's a very, very simple program showing how the assembler works, and then also how the simulator works. Okay, so we've tried our test program, so hopefully you know how this works now. So now we're going to load up the candle program, and we're just going to have a quick look at some of the things here. So this are all our constants. So our slow ramp, we want to start between 10 and 50 and end between 160 and 220. Our fast ramp, we want to start between 40 and 80 and end between 110 and 150. Our so-called random number is 29 to start with, and there's our XOR number. But I've also got this thing where every time we generate a random number, we count, and if it reaches 23, then we just subtract 3. So you can change these numbers. I just wasn't happy with the randomness, I guess, of this, so every so often I just throw a spanner in there, and that just keeps it more interesting. Now all the registers that we saw before were R0 and R1. I've renamed all the ones that I use, so I can just refer to the spanner as being R4 rather than have to remember what all these ones do. So the current storage of the lowest slow value and the highest slow values, R0 and R1. The current storage of the lowest fast value and the highest fast value is R2 and R3. Our spanner, as I said, is in R4, so that's where the count will be. And then we've got a general register in R16, some heavy maths going backwards and forwards between R17 and R18, so I just call them Math 1 and Math 2. Our actual slow ramp, what's actually happening, what PWM signal is in R19, and the fast ramp similarly in R20. The status of the slow ramp, is it rising or falling, is in R21, and the status of the fast ramp, is it rising and falling, so it's just a 1 or a 0 in R22. And finally the actual number, this is one that you'll probably see move pretty regularly, apart from the ramps going up and down. This will be where our random number is generated before it's checked with all these other values. Alright, so let's assemble. Now one thing I probably need to do first is, in the real world, I need to create a delay between changing the PWM signal so that we can actually see it. But that would be mind-numbingly boring to watch that delay happen here in assembler step by step, so I'm just going to comment out the wait cycle here. Alright, we assemble that, and then we simulate, and I'm actually going to put the ports on here as well so we can see what happens to these ports as we go through. Alright, so let's change this update to 1, and that's fine. So we start as we did before, jumping to main. We start by initializing the stack, and then we load the seed into rand num. So if you watch the registers here, 29 should appear over here, so that's where our random number will be generated all the time. Then we need to, first thing is, we need a slow lowest number. So we're going to generate a number where the slow ramp will be starting from. So what we're going to do is we're going to keep throwing the die until we get a value that's between the numbers that we're looking for, which, if you go back up to the start again, for slow is somewhere between 10 and 50. Now remember, they're the decimal values, so we'll just see what that looks like when we load that up into the register. So we step, this is generating our slow low, so we'll need to move these values of 10 and 50, which is OA and 32, into Math 1 and Math 2, and then we roll a random number. So let's do that. So we roll the random number, and what we're going to do now is we're going to say if it's rolled, so that's good. Okay, yep. So this is the bit where this is the linear shift register basically. This is just the 3 or 4 lines that actually do the work for the linear shift register algorithm. So basically, at this stage, it's just rolled LSL, and then we move our spanner into Gen 1, so we see, are we up to 23 basically? What is the current stat of play? And it's currently 0 because this is our first number. So we go, okay, so is 0 more than 23? No. So no spanner required. So we go through to no spanner. And then we go, okay, so we're just going to load that value again of 0, and we're going to increment by 1, and then we're going to say, alright, now the main thing here is this number 52, is it between these two numbers? So we check the low value first. So is it greater than OA? So we step and we go, yeah, it's all good. So then we check the high value and we say, is it lower than 32? So this is a BRCC to check high and a BRCS to check lower. And in this case, it isn't, because 52 is higher than 32, so we need another random number. Okay, so away we go. We're going to LSL again, the random number. This time we can see we've got a register here in the carry, so it's turned 0. So we're good to go again. We check the spanner. It's not greater than 23. So therefore we're going to increment it and move it back. And now we've got a value of A4. So the first thing we say is it greater than OA? So we check that again. Yep, that's good. Is it lower than 32? Nope. So we're back up again. So you can see how that goes. Now, what I'm actually going to do is change this to, let's say, 2000 milliseconds, or every 2 seconds, and I'm just going to run it. Okay, so we'll see what happens as it goes through. Okay, so it's just going to tick over, and we're just going to watch this go at a fairly glacial pace to start with, just going through that process of generating a random number, checking to see whether it's greater than OA but less than 32, incrementing the spanner count each time. So we're down to C3 is not going to cut it, and then we roll a random number again. 86 isn't going to cut it. Okay, so you get the idea. So I'm just going to stop that, and I'm going to change this now to every second, so a little bit of a speed up. Okay, so OD's the one, and it looks good for low, it looks good for high, and so there it is, it's transferred into R0. So we have finally our low ramp. Now our high ramp needs to be between A0 and DC. So we're still looking at the slow ramp here, but we've generated a low value of OD, and we're looking to see now if we can find a value between AO and DC that we can actually put into the high part. So before the ramp start, we need basically where it starts from and where it's going to. And at this stage, looking at the spanner count, we're up to, we've just rolled 7. Alright, so now that we know what we're looking for, I'll just stop this again, increase the speed again, and away we go. So that you should see those numbers go a bit faster now. So there's D0 has been generated as the upper part for the slow ramp. So our initial values for our slow ramp are between 0D and D0. We now have our lower part for our fast ramp, so it's going to start at 2B. You can see our random number count is currently at 0C. Remember, it clicks over at 23, which is what, 17. Let's get our calculator up. So we want, calculator's a bit wide. Can I change it? Nope. Have to put up with that. So we're going to have, we're in hexadecimal. So we need to go into decimal actually and go to 23. Yep, so 17. So it's at 11 at the moment. Still no upper value here for our fast ramp. I'm going to speed up again. So I'm going to go to 100 milliseconds. Alright, so we're still looking for a value between 6e and 9.6 for the upper part of the fast ramp. Okay, bang. Okay, a lot happened then, so I've got to slow this down again. Alright, so let's have a look at these registers. So there's our random number. These two registers, if you recall, say what is the status of the slow ramp and the fast ramp. So they're both rising. These are the actual values of the slow ramp and the fast ramp. So if you remember, it was starting off at OD, the slow ramp, and the fast ramp was starting off at 2B. Alright, and what we're doing now, you can also see that we've actually now got some ports that have been activated there, so we're just going to step through and alright, so we're going to load. Okay, so this is actually putting out the PWM. Just keeps doing it. Okay, now we're going to see if we're rising, and we're going to go up one, so you can see the OD changes to OE because we're rising. Now are we at the end? Nope. So then we check the fast status. What's it doing? It's rising as well. Now actually the subtraction here is actually -2, so our value of 2B is not going to change by 1, it changes by 2. So the fast ramp actually moves faster, not surprisingly. Then you can play with these values as well. Alright, so let's just keep going. And that's the loop finished. Back to outputting. And so on. So really all it's doing now is it's just going to keep going and adding to those values. So I'm going to speed this up again. Okay, and you should see these values rising. So this is going up by 2 each time. This is our fast ramp. This is going up by 1 each time. This is our slow ramp. And the slow ramp is going to keep doing that until it gets to D0. And the fast ramp is going to keep doing that until it gets to 7.6. So, and you can see here that the PWM signals are actually affecting the pins. So that's PB0 and PB1. So that's what's actually being output. And in the real world, when that wait number of milliseconds has been uncommented, so it's back in action, that will create that flickering effect that you can actually see. All right, let's now go to 10 milliseconds. Alright, and you can see the fast ramp's kicked over. It's now falling. So it's falling down towards the value of 50. Now it's rising again. And now it's falling again. So the fast one here will flick on and off pretty quickly from rising to falling. The slow one here, because it's counting up, hasn't even got to the first value yet, which is D0. It's about to reach that. There it goes, and now it's falling. Yeah, so we'll just watch this for a while. In fact, what I might do is speed it up again. Alright, and you can just watch those values and compare what's happening to the actual code. And all those values. So just to go through again what we're looking at here. So we're looking at the lower limit and the upper limit for the slow ramp, lower limit and upper limit for the fast ramp. We're looking at our spanner count here, so how many random numbers have we generated and whether we need to throw a spanner or not. Down here are our working registers. Okay, so that they'll change fairly quickly. Here's our actual slow ramp value, our actual fast ramp value. Here are our status registers to find out whether our ramps are going up with a 1 or down with a 0. and here is where our random number is constantly being generated. So yeah, very useful to match up the code to the registers, to the ports, to see how this chip actually works.